Hello. This video is for chapter 1 of the text, and this text can be found on the class website for this class, and it is titled Expressions and Variables. It's chapter 1, lesson 1. So let's go ahead and we'll start taking a look at it, all right? So I'll go ahead and leave that there. Okay, good. So in this lesson here, we have, I'm trying to find my highlighter. Here we go. So it is lesson 1-1, chapter 1, lesson 1. It is titled Expressions and Variables. And here our objective is that you'll evaluate and write variable expressions. So we have our vocabulary over here on the left. This is numerical expression is one of our vocabulary words. Another is variable expression. What does it mean to evaluate? And finally, what is a variable model? So we have a picture of a blue whale here. Kind of interesting. Whenever I lived in Alaska, I used to see quite a few whales. They weren't blue whales, but seen quite a few of them. Actually had a be out on my 18-foot skiff and sometimes have them breach right up next to the boat 5-10 feet away. Is pretty amazing. But blue whales, during its summer feeding season, a blue whale eats about 4 tons of food every day. So it's 4 tons every day. To find about how many tons of food a blue whale eats in a given number of days, you can multiply the number of days by the number 4, as shown in this table below. So a table, tables have columns and rows. The columns go up and down, and the rows go across. So in this particular table, we have 2 columns and 1, 2, 3, 4, 5 rows. So columns and rows in a table. So in the first column, we have the number of days. What about 1 day, 2 days, 10 days, or what about just using a D for any given number of days, whatever number of days we want that to be? And in the second column, we have tons of food eaten. Well, we get that by if it were 1 day. Well, since it's 4 tons of food every day, we would do 4 times 1. And so for 1 day, we just substitute in the number 1 and get 4 times 1. We want to know about 2 days. Then we'd substitute in the number 2 and get 4 times 2, which would be 8. And what about 10 days? Well, we do the same. We just substitute in the number 10, do 4 times 10, and get 40 tons for 10 days. Or what if we wanted to have an expression that would represent however many days we wanted it to be, that we wanted to know about, and we just use the letter D for the number of days, and we would call that 4 times D. So going on to the next slide here, we see vocabulary. We'll see in the text as we move through the text. This year, all vocabulary is highlighted with yellow highlighting. A lot of times we'll have suggestions and comments and strategies over here on the left-hand side in the margin, and then we'll have some examples. Examples are always in these sections highlighted by these red braces here. So our first vocabulary word that we're finding out about is numerical expression. A numerical expression consists of numbers and operations. Notice that it does not include an equal sign. Later on we'll get to that, and we'll call those equations. But if we don't have an equal sign, if we just have, and I know you've seen an equal sign here and you're saying, huh, what? We just look at the 4D part. We would call that an expression. This would be an expression, 4 times D. And if we just looked at this left side here and took this off of here and have 4 times D, that would be a expression as well. Actually, it'd be an algebraic expression. But right now, we're talking about numerical expressions. They call them variable expressions here. But once you include letters into math, it becomes algebra, and so variable expression, algebraic expression, same thing. A numerical expression consists of numbers and operations. In the table, that table that we looked at back here on this first page here, on the table, the expression 4.10, and this dot is a multiplication sign, and there's a reason for that because, as we see here in the study strategy, when you write a variable expression involving multiplication, avoid using the symbol X, that symbol that you used in the past, like in maybe grade school, you said 3 times 4 or 10 times 6. We don't want to use that X anymore because later on, if we said 10 x6. This could mean 10 times whatever the value of x is times 6. And that would become confusing. So we want to get out of that habit of using the x as a symbol for multiplication, because it may be confused with a variable x, which that leads to what is a variable here. But we'll get to that in just a moment as well. Here we see another way of writing multiplication, and that is 4 and then times 10, and one of the two numbers is in parentheses. We could have put the 4 in parentheses and it would have been the same thing. Usually it's the second value though. And here we do this here, there's no operation sign. So since there's the absence of an operation sign, there's no plus, no minus, no divide, no multiply. So in this case, the absence of an operation sign implies to us that it is indeed multiplication. And the reason for that is we need the parentheses, because if we just did 410, this looks like 410. And we don't want to confuse 4 times 10 with 410. So in that case, we're going to use parentheses to separate them and let the reader know that this means 4 times 10. On to the definition of a variable, because we talked about here, you don't want to use that x sign because it may be confused with the variable x. Well, what is a variable? So a variable is a letter used to represent one or more numbers. Now, my personal definition of a variable is that a variable is a symbol that represents a value that can change. A variable is a symbol that represents a value that can change. Well, that symbol that we use in math, they are letters almost always. I guess you could use a picture of an elephant or a giraffe or a picture of a piece of firewood or whatever if you really wanted to. But in math, we have a tendency to always use letters. So it's a letter or a symbol, and it's used to represent one or more values. Well, one or more values is another way of saying a value that can change. It could be one number, it could be other numbers. It might change. So textbook says a variable is a letter used to represent one or more numbers. I say that a variable is a symbol that represents a value that can change. So if we include some operation signs and numbers along with those variables, then we have a variable expression. So a variable expression consists of, it has numbers in it, it has variables, and it has operations. Remember, it does not have an equal sign. That would be an equation. So an example of that would be, let's say 3 is a number, x is a variable, and we could say plus 7. So in this case, we have numbers, the 3 and the 7. We have a variable right here, in this case the variable x, and we have an operation. We have addition. So also, it doesn't have to be addition. We could just have 3x, right? Take off that plus 7 part. Well, does it still meet all the requirements? There is a number, there is a variable, and indeed we do have an operation. We don't see the multiplication sign there, but we know that there's no multiplication sign there, so it's implied that we're going to multiply. One way you can use a variable expression is to generalize a pattern, as in that table that we had about the whale. The variable expression 4.d represents the amount of food a blue whale can eat in d number of days. So instead of writing days for days, we're just going to use the variable d, let the letter d represent those number of days. You can also write 4.d as 4d, just like I had here with the 3x. So 3 times x, and this is 4 times d. No operation between the number and the variable, so we know that it is, that's right, you guessed it, it is multiplication. Next, we're going to talk about what does it mean to evaluate. So to evaluate a variable expression, we substitute a number for each variable and evaluate the resulting numerical expression. So whenever we substitute in numbers for those variables, we end up with just numbers in the expression. So it goes from being a variable expression to a numerical expression. So with that said, we have an example here in example 1, evaluating a variable expression. To evaluate the expression 4 times d, or like they said up here, 4d, when d equals 120, and remember d is the number of days, so we're talking about 120 days, to find out to find about how many tons of food a blue whale eats in a feeding season of 120 days. So our solution is to go ahead and take the expression 4 times d. We could have left that out and just said 4d is equal to, and then we just substitute in the 120 for the value of d, because here d equals 120, so we just substitute it in. So we substitute 120 for d. Now we go ahead and multiply 4 times 120, and we get 480. So our answer is that a blue whale eats about 480 tons of food in 120 days. On the next slide, in example 2, we see an example of evaluating expressions with, well, 2 variables. So we could have 2 variables, such as x and y. In this case, the first example, in A, we are adding them. And we're told that x is equal to 10 and y is equal to 4. So if we take x plus y, and then we substitute in the 10 for x, notice the color coding of red, and here the y is color-coded with 4 because y equals 4. So then we end up with 10 plus 4. This is a numerical expression. Here we have an algebraic expression, or a, what are the textbook, they call it a variable expression. But we have an algebraic expression here, and we change it over to a numerical expression. We can now go ahead and perform that operation to come up with a solution. That is, that we are evaluating. Whenever you actually do the math to come up with an exact answer, then that is known as evaluating. So 10 plus 4 is 14. On the second example here, we have xy. Well, we see no operation symbol, right? So we know that it is, yes, multiplication. This means x times y. So we're going to substitute in 10 for x because x is equal to 10, and we're going to substitute in 4 for y, because y equals 4. So now we have 10 times 4, and 10 times 4 is 40. We multiply, and indeed we get our solution of 40. So whenever we evaluate each of these expressions for x equals 10 and y equals 4, we actually come up with numbers and tell us what those, what that expression, what the value of the expression is, and actually solving to an answer is known as evaluating. So in our checkpoint here, we could do a couple of these. They say y is 12. So in this case, I would just do 12 plus 8. I'm just simply substituting in the value of y, which is 12, for the y there. And then whenever I do that, 12 plus 8, and I kind of like to work downward, and we could say like that, and then put an equal sign there, but 12 plus 8 is 20. So number 1 has a value of 20 whenever we evaluate it. And what about over here? Number 3, y minus x. Well, y is 12. The operation is subtraction, and x is equal to 6. So in this case, it would equal 12 minus 6, and 12 minus 6 is indeed 6. And then finally, we have this one here where x is 6. And I'm going to use parentheses to separate that so that we don't think we're talking about 612. We're talking about 6 times 12, and 6 times 12, well, that's the same as 6, think of it this way, 6 times 10, and also 6 times 2, and in this case, we would end up with, well, 6 times 10 is 60, and 6 times 2 is 12, and then 60 plus 12 is 72. So a little bit of my mental math there of how I got to the answer of 72. 6 times 12 is 72. Looking at our next page, we have a watch out notification over here. So I think we'll get to that after we read this part here. So let's go ahead and kind of put the watch out to the side, and let's look at this first paragraph above this table. Again, it's a table because it has columns and it has rows, right? So we use tables to organize information. So writing variable expressions, you can solve a real-world problem by creating a verbal model and using it to write a variable expression. A verbal model describes a problem using words as labels and using math symbols to relate the words. The table shows common words and phrases that indicate mathematical operations. Remember, we have 4 operations, and those are addition, subtraction, multiplication, and division. And all tables should have a title, so our title for our table here is common words and phrases that indicate operations. Our watch out over here is in regards to subtraction and division. Get to that in a moment, so let's go ahead and cover that now. So order is important in subtraction and division expressions. The difference of a number and 7 means n minus 7, not 7 minus n. So let's say that number were the difference between a number, so let's say 10. So if this number here were 10, and we said difference between 10 and 7 means 10 minus 7, not 7 minus 10. Because 10 minus 7 would be 3, whereas 7 minus 10 would be negative 3, and 3 and negative 3 are not the same value. So the quotient, and that means divide, we'll see that over here, right there, the word quotient. The quotient of a number and 5 means n over 5, not 5 over n. And this fraction here, we're going to see on the next page that fractions are actually division problems. All fractions are a division problem. We can always simplify a fraction by using the operation of division. So let's look at some common words and phrases. For addition, first is plus. Let's use the numbers 3 and 2. That seems pretty simple. 3 plus 2. Or the sum of 3 and 2. Sum means to add. Or 3 increased by 2. So we could use the phrase increased by. Or what is the total of 3 and 2? So total is a word we would use for addition. How about 3 more than 2? That would still be 3 plus 2. Or 3 added to 2. We would still add 3 and 2 together, and all these, of course, would have the sum of 5. What about subtraction? Let's do, well, 10 and 7 worked well, so let's talk about that. We could say 10 minus 7. Or we could say, what is the difference of 10 and 7? Now, this is one of those ones where the order makes difference. We say, what's the difference of 10 and 7? The first number I said comes first, then the minus sign, and then the second number, which the difference of 7 and 10 would be different. So, or how about 10 decreased by 7? So we start with 10, we're going to decrease it. That means to take away. Notice take away is not listed in here, so take away is another phrase that we would use for subtraction. Or 7 fewer than 10. That'd still be 10 minus 7. 7 less than 10. So let's see, 7 fewer than 10. 7 came first, then 10. We would actually write that 10 minus 7. And 7 less than 10. Even though we said 7 first and 10 second, we would have to flip it around and write the 10 first and say 10 minus 7 or 10 less than 7. Or 7 subtracted from 10. Notice that I said the 7 first and the 10 second, but still we would start with 10 and subtract 7. So subtraction is one of those ones you have to be careful with of what order you put it in. Because like the first one, 10 minus 7. Notice I said 10 first and 7 came second. Or the difference of 10 and 7. 10 comes first, 7 second. You spend a lot of time on this. It's a really tricky one for students. I know sometimes they get hung up on the subtraction section. It's kind of like the division, but not near as much. Multiplication, let's do 4 and 5. 4 times 5. We could also say 5 times 4, so the order doesn't matter there. And later on we'll learn that's because multiplication has what's known as the commutative property. The order doesn't matter. We could communicate or flip them around. I was using 4 and 5, right? Yep. So the product of 4 and 5. Or we could say 4 multiplied by 5. Another one is of. We wouldn't say 4 of 5. Of is one that we use a lot in whenever we deal with percentages. Like we would say 20% of 120, right? Well, we'd actually have to change this 20% to a decimal, which would be 0.2. Of becomes multiplication. And since it's multiplication, we don't have to write a sign, right? And we just put this 120 in there. So later on, whenever we deal with percentages, of will be a very, very common word that we use. And then finally, division. Let's go with 20 divided by 4. So 20 divided by 4 would be 5. So we'd say 20 divided by, that lets us know to divide. I mean, divide, division, the word's right there, right? Or let me see, 4 divided into 20. Notice that it was backwards. Here we said 20 divided by 4. Here we would say 20 divided, or let's see, 20 divided by 4. Here we would say 4 divided into 20. Notice it's kind of like backwards. Let me get my pen here and I'll actually write that. 20 divided by 4. So this would be 20 divided by 4. Notice I said 20 first and 4 second, and I wrote 20 first and 4 second, the 4 after the 20. On the next one, here we would say 4 divided into 20. Well, we would still want that as 20 over 4, and that would be 4 divided into 20, or we could say 20 divided by 4, which was the first example. The other one is the quotient of. Quotient of, and this one's kind of tricky too. We would say the quotient of 20 and 4. We want the 20 on top, so we say it first, and here we had the 4. If we said it the other way around, we said the quotient of 4 and 20, then we would write this as 4 over 20, which are two totally different things. 4 over 20 equals 5, and here they're both divisible by 4, so we end up with 1/5. Whereas 1 equals 5, the other one equals 1/5, or 1 over 5. All right. And our third example here in reading algebra, when you write a variable expression using division, use a fraction bar instead of the division symbol. That's that line with the 2 dots. For example, write the quotient of n and 12. Well, they said n first, so it goes up top, 12 goes down bottom. The top is the numerator, the bottom is the denominator. We have a numerator and a denominator separated by a fraction bar. All fractions are division, and here, since we say the quotient of n and 12, the order does matter. So baseball. You plan to divide the 120 players in a baseball league into teams with the same number of players. Use a verbal model to write a variable expression for the number of teams if you know the number of players on each team. So our solution is to let P represent the number of players. So instead of writing out players, we're just going to let P represent the number of players. The word divide indicates division. We see that right up here. Is that in there? Yep, you plan to divide. There's that word divide, so it's telling us the operation that we're going to use. So to find out the number of teams, we're going to take the number of players in the league, which we're told is 120. We're going to divide it, because it tells us divide, by the number of players on each team. And we don't necessarily know how many that could be 20, right? 120 divided by, but 20 players on each team. Now, 20 players would be a good-sized baseball team. I guess that would work. What, you need 9 guys on the field, I think it is. So the answer is that the number of teams is 20 divided by P, but like the reading algebra hint says, we're going to use a fraction, and that's 20 divided by P. You could almost read this fraction bar, not almost, you can. You can read this fraction bar as division. That's 20 divided by P, or we could say 20 over P. Either way, 120 is the numerator, and P, the number of players, is the denominator. So we have some practice here. We say identify the variable in the expression 21 plus D. Well, we know that variables are symbols that represent a value that can change. So this D is the symbol, so D is the variable that's in this expression. Compare and contrast the expressions 2 plus X and 2 plus 3. Well, they're both expressions because they have numbers and operations. So the first one, let's go to the second one first. The second one only has numbers and operations, so it is a numerical expression. However, we have a variable here, so 2 plus X not only becomes an expression, but it is an algebraic expression, or as this text calls it, a variable expression. I prefer algebraic expression. Skill check, evaluate the expression when X equals 4. So evaluate means to actually come up with a number. So let's do number 4 here. If X is 4, we'd have 4 plus 7. We just substitute in the value of X, the value of 4 for X, and this equals 11. So 4 would be 11. On the other one, we're doing 32 over x, so 32. I say over, but it's actually divided by, in this case, 4. And 32 divided by 4 is, I believe, 8, right? Correct. 8. 8 times 8 is 16. Double 16, we get 32. To this day, I still have to think to myself, 8 times 4, 8 and 8, 16, 6 6 is 2, that's the 12, so 32. It does it fast in my head, but still to this day, I still have to do that. And then finally, evaluate the expression whenever we have two variables, and we have values for each of them. First one, m equals 5. The second one, n equals 6. So let's look at the first one here. We're going to substitute for the n. We're going to go ahead and substitute the value of 6 over 2, or 6 divided by 2, and 6 divided by 2 equals 3. 2 will go into 6 3 times. The other one here, n equals 6, m equals 5, and 6 minus 5 equals 1. So there you have it. That is the total presentation for, let's go back. There we go. That's my presentation for Chapter 1, Lesson 1. It was titled Expressions and Variables, and we learned how to evaluate and write variable expressions. All this is matched up with activities that you'll find at the class website. So go ahead, check out the videos for those activities. They're related pretty much to everything that we've done here in this first lesson. Thank you.